Hi, I'm Mr. V. Today we're talking about illustrative mathematics, which is our textbook. We're in Unit 5 of Geometry. This is called Solid Geometry, and this is Lesson 4, Scaling and Area. The objective is by the end of the lesson, you should be able to say, I know that when figures are scaled by or dilated by a factor of k, their areas are multiplied by k squared. So we started off with this question, which is what has a number times itself is equal to 25, and that's 5. 5 times 5 is 25. Number multiplied by itself is equal to 81. That would be 9. 9 times 9 is 81. And what number multiplied by itself is equal to 10? And if I go to my whiteboard here, and I have numbers equal to 10, so when I multiply the number x, I don't know what the number is, times x, I'll equal to 10. Well, this is just x squared. To find out what x is, I'll do the inverse operation, which is to take the square root of both sides. And when I do that, I get the square root of 10. Now, the square root of 10, square root of 9 is 3. Square root of 16 is 4. So it's 3 point something. And I'm not sure what it is, but 3 point something is an approximation. The square root of 10 is the exact number. If I wanted to find the exact number, I could use a calculator, such as the Desmos calculator. And I could type in square root of 10. And here I get 3.1622773. This is still an approximation. So it's about 3.2. So I could say this is approximately, using the approximate symbol, 2 tildes on top of each other, about 3.2. That's to one decimal place. So another word for multiplying a number by itself is called squaring a number. We represent this with an exponent of 2. So when you have an exponent, you have the base and you have the exponent, which is up here. You multiply the base by itself the number of times of the exponent. So if the exponent is 2, you multiply the base by itself 2 times. So this would be x squared would be x times x. Okay. Number 25 is called a perfect square. Why? Because its base of its square root is a whole number. And there are only a few of these. There's only a limited number of whole numbers. There's an infinite number that are not. So 10, square root of 10 is about 3.2. Now, here's a rectangle. And what we wanted to do was to square it. First of all, what's its area? If you were to write the area in this box, you would have, I want you to write the formula, substitute the values, and solve. So we have the area is equal to the length times the width. That's the formula. We substitute the values of 5 times 2, and we get 10. And we could put units squared if you wanted to, because it's got length component and a width component. Now the next question that goes with this is, what if we dilate it by a factor of 3 and then find the area? So if I make this 3 times as long, I would draw a line. I'm going to do a line. I'm going to do a line from point A going in each way of each of the vertices. I'll go this way, I'll go this way, and I'll go this way. And when I do this, you can see that if I'm going to go 3 times as far as it is from A to B, we go 5. 1, 2, 3, 4, 5. I should put this tool. And 1, 2, 3, 4. 1, 2, 3, 4, 5. Right here. If I go in the Y direction, I'll go 2, 2, and 2. Now I've done it 3 times. And if I go this direction, I go up 2, across 5, up 2, across 5, up 2, across, to the right 5. And I get this big picture right here. It's going to be 6 tall and 15 long. So again, my area is equal to length times width. So I have 6 times 15, or 15 times 6, and I get 90. But wait a minute, this had an area of 10, and I'm scaling it by a scale factor of 3. So my scale factor is 3. Why is this got 6 to 9 times the area? In fact, if I were to make it like this, I can show you these 9 of these. Man, why is it 9? 9 of these areas that are like this little blue. All I did was scale. Well, I've scaled the length and I've scaled the width. So the area is, if we have the length of my second figure is equal to the scale factor times my length of my original, notice that the area is going to equal to the scale factor squared times the area. And that's what we're shooting for in today's lesson. So for instance, in the first one, we had an area of 10. And my scale factor by which it changed by 1. When I did this by 3, my area was 90 and a scale factor of 9. If I do a scale factor of 2, so back to this drawing, if I were to do this in a different color, say orange, did it by a scale factor of 2, my area would be 10 times 4, which is 10 times 4 is 40. So I could fill this out to 40. And that's a scale factor of 4. Notice the 4 here is the same as my 2 squared. 1 squared. 3, right here, 3 squared. If you do these other numbers, you can do this as well. And you'll find that if I'm going smaller, it works with fractions. It also works with this. So it works with 2.5. That would be 6.25. All right. Scaling up a rectangle. Write an expression for the area of the rectangle. Let me do this on my whiteboard. So just a moment. Make this smaller and copy this over to my whiteboard so you can see it. When we write the expression for the area of the rectangle using length and width, if the area is equal to length times width. When we imagine dilating a length of 1 and a width of 2, we would have our length is equal to k times 1, and our width is equal to, when we scale it up by k, times 2. Now our area would equal to, our new area, this is our second area, would equal to k times 1 times k times 2, which is equal to 2k squared. K squared, because this would be 1 times 2, which is equal to 2. This is times k squared. My conclusion is that when I scale it, whether it's scaling up or down, whatever the k values, it's less between 0 and 1, or if it's greater than 1, the area is going to be proportional to the scale factor squared. Here we have a question. The image shows a dilation. Scale factors 1, 2, 3, and 4. Why are each of these odd? So if I go from 1 to scale factor of 2, I'm going to go from one figure to 4. It's going to be an odd number that I add. If I go from here to this one, I'm going to go from 4 to 9. It's going to be an odd number that I add. If I go from 9 to 16, it's going to be an odd number that I add at 7, and so forth. And your question is to why. And this is part of the more, it's a little bit deeper discussion. Here we have some things to ask ourselves about. The goal of this is to establish that when you scale a rectangle by a factor of k, its result for the area is by k squared. That's the whole big idea. If you can understand that, understand where it comes from. Notice it has a length component and a width component. When you scale the length by k and you scale the width by k, that's k squared. That's where you get the k squared from. So here's some questions for you to ponder. And then we have this weird looking shape. And the person said, well, wait a minute, I could make this into a bunch of rectangles and I could scale up each of the rectangles. And how does it work with it? And of course, this is going to be the same thing. So if you had a circle with an area of 20 square inches and it's dilated by a scale factor of 6, what is the area of the image? So if I have a circle and it's dilated by a scale factor of 6. So if this has a radius of 1, this has a radius of 6. How many times larger is the new one going to be? Well, pi r squared is going to be the area. So I could have pi times 1 squared. And here we've got 6. So pi times 6 squared. This is going to be 36 times larger in the area if I make that sentence. So if I had a circle with an area of 20 and I multiplied it by 36 because it's going to be this scale factor squared. So this is 20 times k squared, 20 times 6 squared, 20 times 36. I'm going to get 720. Is that what we asked for? 720. Yeah. And for the lesson synthesis, be sure you can explain that the scale factor is proportional of an area is proportional to the scale factor squared, the area. And whether that's smaller than 1 or whether it's larger than 1, it still works the same. A 6 by 10 rectangle is dilated by a factor of 3. What is the area of the dilated by? Area of the this would be 60. If you multiply it times 3 squared, which would be 60 times 9, would be 540. Here's a lesson summary. You can read about this on your own in this Desmos activity. And then there's the how did you feel about what we did today? So that's all I have. Good luck and success.